write a few notes out with me if you will, and let's go from there. All right. I alluded to this earlier, this unit, and that is the whole point of this is to turn heat into work. But when we do that, a lot of the heat is lost. It's exhausted, kind of like me right now. We did this beautiful example back at the beginning when we started looking at the math, and we found that 500 joules of work was done by the gas, and 500 joules total of heat was converted into that work. Okay. But when that happened, a whole heck of a lot of heat was added in this problem, 3,750, and only 500 joules of that actually converted into work. The rest of that was lost in exhaust, moved out of the system. So that's not the most efficient way, maybe, of converting heat into work. Well, there's a guy by the name of Carnot, C-A-R-N-O-T, Carnot, who came up with a cycle that would be the most efficient thermodynamic process. And if we go through that process, A, B, C to D, he found that the most efficient process would be from A to B would be isothermal expansion. It stays on the same isotherm. From B to C would be adiabatic expansion. C to D would be isothermal compression. And D to A would be adiabatic compression. Now here's the thing. From A to B, the temperature stayed the same, but somehow the piston expanded. Heat was added to the system during process AB. B to C, no heat was added because it's adiabatic, no heat. From C to D, work was done on the gas by compressing it, but it still stayed the same temperature. So heat must have flowed out during that process. That's where the exhaust occurred. And then D to A is adiabatic, no heat. So the QH would be the heat that was added at the high temperature. That's why it's QH. Okay. QL would be the heat lost or exhausted at the low temperature. Okay. Now, a couple quick notes about the Carnot cycle. It's theoretically the most efficient thermodynamic process possible. And second, it is supposed to be fully reversible, meaning if instead of going A, B, C, D, A, we went D, C, B, A, D, I think that was reverse, we would end up, we could do that. It's a reversible process. Just means all the signs are flipped. Okay, Carnot cycle is theoretically the most efficient and it's reversible. Now, if we look at efficiency, the efficiency, sometimes abbreviated as E, sometimes it's lowercase e, sometimes it's given as a decimal like 0.2, or sometimes it's a percentage, 20%. Whatever, you guys are smart. Come on, you're going to college next year. You can handle that. So the efficiency would be the work done by the gas divided by the heat that was added to the gas. I'm going to do it. I'm going to go back to that example again really quick, where right here we had 3,750 joules of heat added to the system, and we got 500 joules of work out of it. So the efficiency, I don't have a lot of space, but I'm going to say the efficiency would be the work over the heat added to the system. So that's going to be 500 divided by 3,750. And I wish I'd plug that in first. Oh, I got 0.133. So what does that mean? That means that this cycle was 13.3 efficient. Cool? All right, so let's go back to those efficiency notes. So one way to calculate efficiency is the work done divided by the heat added. Now look, the work done is really just the difference in that was absorbed by the system and was lost. So I could substitute in for work QH minus QL. Now, if I do, I can simplify that. It just becomes 1 minus QL divided by QH. Another way to find the efficiency. But you know what? There's an even better way. And the Carnot Cycle gives it to us. The maximum efficiency of a system is dependent upon the temperatures that it runs at high and low. So the Carnot efficiency, the maximum possible efficiency you could ever have, is related to the temperatures. And it's going to be 1 minus temperature low divided by temperature high. What the heck does that mean? It means that the greater the difference in temperature, the more efficient the engine can be. Yeah, that's it. That's it. So the greater the difference from that low temperature to the high temperature, the greater that difference, the more efficient this Carnot engine could be. This is an idealized situation. So if you have an engine that runs at the low temperature of 400 and a high temperature of 500, we could really easily calculate the maximum Carnot efficiency. Yeah, I know the answer. 1 minus, you got it, 0.5 or 50%. What this means is that the maximum efficiency of this engine could possibly be is only 50%. That doesn't even include things like friction. Okay? Friction is included when we do the regular efficiency. So, I'm cutting it there. If you didn't like my explanation, go and look it up in the book. Thanks, guys. Hope you're good. Tomorrow's quiz. It's open notes. It's open book. It's open Google. Look it up. Ace it. And then that may be your last big summative, maybe, in your high school physics career. Hope you guys are good. Thank you for bearing with me. I know this is getting a little long. Tomorrow, problems, and then we review. Take care.